Seen at this point how to connect the data in a table to the points on a graph, right? Just by plotting each as an ordered pair. This one right here, for example, would be what you get if you went out to 105 in the x direction and then up to 200 in the y direction. And the coordinates of that point would be 105, 200. But the real exciting part of what we can do with this kind of information is what we'd like to do is find an equation that relates together the value of each of these x values together with the value of its corresponding y in a way that's true for each one of the data points. Because what we observed, to remind you of where we were at in this conversation, what we observed is that all of these points have a common pattern that unites them, at least in the graph, because they all lie on the same straight line. That's the first observation that we made. And the second observation was that we could reason our way into defining a slope for this real line, this straight line, rather. And the way that we did that was by dividing the differences in the y values along this line, so y2 minus y1, divided by the differences in the x values, corresponding x values, x2 minus x1, and that ratio, that we call m, is going to be the same regardless of which 2 points we choose, either from the table or from the graph. As long as we do this process the same with any pair of points along this line, we're going to come out with the same answer. And for this particular line, we decided, remember, that this slope was -10. Where would that -10 have come from? Well, again, pick any 2 points from our list. Let's say maybe I picked these two, just for the sake of argument. And then just subtract. Let's say we do 400 minus 700. There's the differences in the y's. Let me color code those according to how I have them in the equation. 400 minus 700. That's -300. And then if I do the same thing with my two x values, 85 minus 55, that's going to give me 30. And so to find the slope, I would just divide this difference divided by that difference. And that's where my -10 is coming from. -300 divided by +30. And that's -10. And at the end of class last time, we also gave an interpretation to what this -10 means. If we think about it as a fraction, -10 over 1, then we can think of the -10 upstairs as being a difference in y values. And since the y values are the prices of these iPhones, this would mean that we're looking at a $10 drop. For every $10 drop in price, the denominator here relates to a difference in the x values. The x values are how many millions of iPhones that we're selling. And so what we'd be saying here is that 1 million more sales would take place. So that's what the meaning of that -10 is. Again, that slope is a comparison between changes in the y quantity and changes in the x quantity. So that's where we were at the end of class on Monday. And we got really what I would think of as kind of the first important formula when we're thinking about how to get towards finding a formula that actually relates the x and y coordinates of the points on this line. Along the way, we find this first important observation, right, that we know now how to find an equation, sorry, not an equation, we know how to find the slope between any 2 points on a graph, y2 minus y1 over x2 minus x1. But that doesn't get us all the way to where we're ultimately going, which is I want an equation that tells me how to turn these x values into these y values. So that's where we need to go next. So we decided, for this line, that our slope is -10. So I'll just put -10 here. And then I'll write this as y2 minus y1 over x2 minus x1. So now I want to use this to somehow find an equation that, again, is going to relate together any of the x values on this list with its corresponding y values. So here's how I'm going to do it. I'm going to take any single specific point on my line. Maybe I'll take this one right here. Let's say, just for the sake of argument. This is 55, 700. And I'm going to call that point my x1, y1. So I'm going to just think about what it would look like to plug in those specific values into this slope formula for a second. So in place of x1, I'm going to have 55. In place of y1, I'm going to have 700. But then if our goal is to find a relationship not just between the 7 points on the line, x values and y values that we have listed, sorry, 6. We have 6 points here, and we know how their x and y values are related, but what we really want is we really want to know how every single arbitrary point on this line has a relationship between its x value and its y value. So what I'm really interested in is the point whose coordinates are generically written as x comma y. So I'm going to use that notation in place of my x2 and y2 in my slope formula. So in other words, we're now going to abuse this slope formula a little bit as a way of relating together not two specific points on this line to find a slope, but rather relating one specific point with one unknown point, one arbitrary point that we're just going to call y comma x. And what that does for me is it now gives me an equation, right? It's an equal sign and an expression on either side, and that equation has both x and y in it. And that x and that y can represent absolutely any point on this line. They don't have to represent one of the points that we already know. They can just as well represent one of the points that we don't know. And that's the power of algebra, right? Is that this relationship is going to hold for all the infinitely many points on this line, not just the 6 that we already know. And all we have to do now is look at this weird-looking equation and see if we can figure out a way to rearrange it to tell us something a little bit more easy to work with about the relationship between x and y. In particular, what we'd like to do is write it in a form where if I plug in an x, then it's really easy to calculate the y. That's usually what we search for when we rearrange this equation. And the way to do that would be to try to get the y in this equation by itself. So now we've turned it into an algebra problem. I've got an equation on the right-hand side. It has an x and a y in it. I'm going to try and get the y alone. If I can get the y alone, then we have an equation that's a lot easier to use. So what do you think I can do here? If my goal is to get this y right here to be by itself, maybe where should I start? Here's an idea. This negative 10 here, it's a whole number, but the thing on the right-hand side is a fraction. So it might be easier for us if we just turn this negative 10 into a fraction, the way that we always do with whole numbers, negative 10 over 1. Right? And now I have two fractions that are equal to one another, but their denominators are different. And so since their denominators are different, their numerators have to be different in exactly the same way. Two fractions are equal if whatever factor differentiates their denominators also differentiates their numerators, right? If the denominators of one are half the denominator of the other, then the numerators have to have that same relationship, right? So the fact that these two fractions are equal means that if I obtain the right one from the left one by multiplying by x minus 55, this is going to look a little bit weird for a second, then that must also mean that I have that same relationship in the numerator, that I obtain the numerator on the right from the numerator on the left by multiplying by that same quantity, x minus 55. So all of this is to say that we can rearrange this equation in the following way. Looking at just the numerators, the denominators is really obvious. 1 times x minus 55 gives me x minus 55. And so the real interesting thing is that in the numerator, what it's telling me is that y minus 700 is the same thing as this numerator, negative 10, times the quantity x minus 55. So that's just given us a way to simplify this equation, x minus 55. And this now is an equation that relates together y and x, and now it doesn't have a nasty fraction that y and x are trapped in. Now it just has kind of everything written as what look like whole number expressions, right? Whole expressions rather than rational expressions. So this is kind of a nice equation. It's nice enough that we actually give it a name. We call this the point-slope equation for this line. And it's called the point-slope equation for this line because from this form of the equation we can easily identify both the slope of this line, but also we can identify the coordinates of one of the line's points. First of all, where do you see the slope of this equation inside the equation? Well, remembering that the slope was -10, here it is right there. Right? So it's called the point-slope equation because, for one thing, the slope is visible right here, calling the slope n. But then we call it the point-slope equation because we can also see the coordinates of this point, 55, 700. Those coordinates are staring at us in the face right here and here. And so the 55 and the 700 are the coordinates, x1, y1, of one of the points on our line. And then everything else is part of the template that makes up this equation, m times the quantity x minus x1. So the point-slope form of an equation gives us a template that allows us to, given any slope, so once we know the slope of the line that we want, and given the coordinates of any point on that line, x1, y1, all we have to do is put that slope and the coordinates of that point into this equation template, and we get an equation for that linear relationship. And that puts us kind of at our second big milestone in this process. All we need in order to find the point-slope equation for a line is, as its name suggests, any point and the slope. So this is great. Okay. This now would, in some contexts, be an acceptable answer to the question, what is an equation for the line that has this as its data table? One answer to that question would be y minus 700 equals -10 x minus 55. And you might just leave it like that, depending on the context. So often when I teach calculus, for example, this might be good enough for me in that context. And one of the things you do a lot of in calculus, especially in the first semester of calculus, is you find equations for lines. Because it turns out that if you know a line, it turns out that you know a lot. And you can use lines to approximate behavior of more complicated functions. And so coming up with an equation that describes that behavior is a really powerful tool. So you do this a lot in calculus. And in calculus, you'll usually know what the slope is that you want, and you'll know what a point is that you want on that line. And so this point-slope template is a great tool. It lets you jump directly to an equation which describes the relationship between all the points, x and y coordinates on this line. But very often we want to go one step further. One of the reasons is that the whole any point stipulation here means that if I write down this equation, I have one possible equation for this line, but that relied upon me choosing this point, 55, 700, to build my equation. If I had picked a different point, let's suppose that I had picked, I don't know, maybe I picked this one instead. This blue point here has the coordinates 85, 400. That's also a point on this line. And you might imagine that if I had chosen this point, then the equation that I would have gotten here in point-slope form would actually be different. And you'd be right. It would look different. It would be y minus 400 equals -10 times x minus 85. Right? And that, too, would be a correct equation for this line. So when we use point-slope, there's actually infinitely many correct answers that we could have that follow this equation template, which is kind of nice for you from a flexibility standpoint. It means you get to choose any point that you want to get this process started, whichever one happens to be the most convenient. But from the point of view of having a standard answer that we can easily look at and assess whether or not it's correct, we usually like to go one step further. The other drawback for this version of the equation is that it's got some algebra that's not completely simplified. I've got some parentheses over here that are not simplified, and the y is not yet completely by itself. So what we'll do to take that last step is continue this process from the point slope equation to solve for y. Get the y by itself and simplify. So I'm going to start from this version of the point slope equation that we just found, y minus 400 equals negative 10 times x minus 85. And then I'm going to try to get that y alone. What's the first thing I'd want to do? It would be efficient for us to get the y by itself to add 400 to both sides. So if I do that, now my y is by itself, and on the right-hand side I have negative 10 times x minus 85, in parentheses, plus 400. Okay, now the y is alone, but now my arithmetic on the right-hand side is not completely simplified. So let's simplify it. How do I simplify this expression that I have on the right? What would be the first thing you'd want to do there? Distribute the 10. Distribute this multiplication by negative 10 across the subtraction, x minus 85. And so that's going to give me negative 10x plus 850 after I do that distribution. I still have y equals on the left-hand side. And then I have plus 400. And then what's the only step that I have remaining? I can add together 850 plus 400 and make that a single number. And what I get at the end of that process is an equation, y equals negative 10x plus 1250. That now has y by itself, but also has completely simplified arithmetic on the other side. And this is a super useful tool, because this tool now is an equation that also relates together x and y, but it does so in a way where if I specify a value for x, I don't have very much work to do to figure out what the value of y that corresponds to it should be. All I have to do is multiply that number by negative 10 and add 1250 to it, and I'm done. We can check to make sure that the x's and y's that we have over here in our table actually work for that. Let's say I pick 35, 900. Let's just double check that if x is 35, then y is negative 10 times 35 plus 1250. That's negative 350 plus 1250. And when I add those together, I get 900. And sure enough, that was the y value associated with 35. So as with a lot of things in algebra, we can always go back and check and make sure that our answer is consistent with the question. Right? That it's consistent, this equation is consistent with the data table, which is consistent with the graph. Those three things need to be telling the same story, even though they all tell them in slightly different ways. And this version of the equation with simplified arithmetic and with y by itself is an example of a template that's usually the one that people remember the most keenly from their earlier algebra experiences. It's called the Slope-Intercept equation for this line. And it's called the Slope-Intercept equation because in it we can easily, again, identify where the slope is. The slope is right here. Right? It happens to be attached to our x in this version. So m ends up there. And then there's another number that we haven't seen show up yet until now, 1250. Where, by the way, does that 1250 show up on our graph? What value would I have to put in for x in this equation in order that the value of y turned out to be 1250? In other words, if I wanted to just get this 1250 by itself and not have the other term here, what would I have to plug in for x to make this piece disappear? If I plug in a 0 for x, this first term is going to disappear. And that actually gives us our answer to how do we find this 1250 in context. Because if in my data table x were made to be 0, then the value of y would be 1,250. That means that this is the coordinates, these are the coordinates, of a point on this line. It's a point that we haven't drawn in yet, but it has to be there nonetheless. The point 0, 1250. And 0, 1250 we would find on this graph by starting at the origin and neither moving to the left or to the right because x is 0, but simply moving up 1,250 units. That would put it actually right up here. So this yellow point has to be a point on our line, and sure enough, if we extend our red line far enough, it does actually go through that point. And the fact that this is called the slope-intercept equation argues for what we call this point. The point 0, 1250 is called the y-intercept. It's the point on this line where the line intersects the y-axis being this vertical line here at x equals 0. So that's the intercept that's part of our slope-intercept equation. And for, again, some historical reasons, we end up calling that number b. I'm just giving it a name of b. And so what that means is that the template for a slope-intercept equation is this familiar animal, y equals mx plus b. It tells me that in order to find an equation for a line using two pieces of data, I still need to know what the slope is. That's always going to be my m. Right? But then in this format, I also supply the equation with the coordinate, the y-coordinate of the y-intercept, the place where this line intersects the vertical line at x equals 0. And the slope-intercept equation is the one that I feel like people tend to remember the most. It gets kind of drilled into your memory when you take introductory algebra courses. And it's also just the most compact, right? It's the easiest to use form of a linear equation. So that's the one that people tend to carry with them out of their prior experiences with courses in algebra. And it's, it's a pretty big deal, so we're going to make it our friend as well. So these are the three tools that I think are the most important tools to take away from this whole topic, right? And they're arranged in order. First thing that you need to be able to do is, given 2 points, to find the slope of the line that goes between those 2 points. And that's what this first equation does for you. Subtract the y's, subtract the x's in the same order, and divide the former by the latter. Right? That'll give you the slope. Remember always that the y's are on top. It's an easy thing to screw up. And using that slope and the coordinates of any single point, you can build a point slope equation for the line, as we did. That's what led us to this equation. But then, simplifying out that equation completely will lead us down to the simplest version, which is the slope-intercept equation.